We have looked at the motor. Now let us look at the track on which this motor will move. So the track is nothing but actin. Actin is a protein with 42 kilodalton. Dalton is the molecular weight of the monomeric unit. In the monomeric units is a globular protein, therefore it is called G-actin. Now the G-actin can come together. So they will come together and it will form a fibrous structure that is called F-actin. Now coming together of G-actin is promoted by a protein known as ARP, that is actin related protein. There are many ARPs. 2 and 3 are important for this fibrous formation of the F-actin. What exactly is the role of this ARP protein? It helps the G-actin molecule to come together. You understand that when two of them come together, when two subunits are coming together, there will be several forces of attraction. And this is overcome with the help of this ARP protein. They are coming together, and you know that when there are 3 molecules joining together, it will overcome the resistance for assembly. So this way the F-actin molecule is formed, which forms a kind of a fibrous structure. Let us a little more closely look at this particular assembly. If you look at the assembly, in the F-actin molecule, roughly about 7 of them, it will join together, it will form a kind of a wire. So it forms a helical structure, it forms one wire, and it is a dimeric form. So there is a second wire that is forming, it forms a kind of a helical structure. Each of these is, you can consider, each of these is the G-actin molecule joining together. Now, in order to stabilize this, you will find the tropomyosin molecule running along with that. So this is the tropomyosin molecule that will run. Okay, this is actin, this is a tropomyosin. Okay, tropomyosin. Along with the tropomyosin, you will find troponin also. Now, troponin, there are 3 such units in the troponin. The 3 such units of troponin are troponin I, troponin C, which is a calcium binding, and troponin T. So these are the troponins. So troponin T, I, and troponin C. So these troponin molecules, this forms the kind of assembly in the actin filament. So on this only the motor protein will run. Now we have been looking at how exactly this polymerization of actin occurs. Now the polymerization of actin is very significant, and elaborate study has been carried out about the polymerization of actin filament. In the polymerization of actin filament, as we have seen that initially if there is a small polymer, it is much easy to add monomeric units to actin filament. Assume that this is an existing actin filament. Now to this we are adding a new subunit. Now this subunit, it is to be added to this. Now subunit can be added. Now remember that every actin will have a positive end as well as a negative end. Not negative, a minus end. So if the positive end means it is the fast growing region of actin, and in the minus end it means it is the slow growing region of actin. Fast growing means monomeric units can be added fast, and slow growing means monomeric units will be added slowly. And when you add this when you add this, what will happen to this is, this is the unit we had, okay, the existing unit. To that, this monomer unit is attached, a new unit is attached. So therefore, if this is n number of residues, this becomes n plus 1 number of residues. So if the kinetic constant of this addition is what we call it the K on, it is added. And at the same time, now remember that an ATP hydrolysis is needed. Every monomeric unit will be bound to an ATP molecule. As it is getting added, it gets hydrolyzed into an ADP molecule. And with an ADP bound actin it is unstable, there is a possibility that it can get dissociated also. So that dissociation is what we call it K off. If the rate constant for addition is in the unit of per mole per second. If the rate constant for K off is per second. Now, if the addition of a monomeric unit, that is purely dependent on concentration. Addition depends on the concentration. If concentration of free monomeric units, if there are more free monomeric units, more addition will occur. Whereas the removal, as you know, it is not dependent on the concentration of the monomeric unit. Let us draw a figure in order to understand this process of addition. Now, this is the length of the polymer, and this is against time. Okay, this is time. You will see that initially there is something called a lag phase. This is the lag phase. Why there is a lag phase? Because the monomeric units must come together. It has to overcome the resistance. So there is a lag phase. After that, once the nucleation begins, you will see that there is something called a growth phase. Rapid addition taking place. After the rapid addition, you will see there is an equilibrium phase. So these are the three phases that you see in the addition of in the assembly of actin filaments. Now, when you look at the equilibrium phase, what is important for us to see is that the K on concentration is equal to the K off concentration. In other words, K off divided by K on, that concentration is what we call the critical concentration. So at the critical concentration, if the number of subunits which are added is equal to the number of subunits that are removed. So this is the critical concentration, which is very important for the polymerization of actin filaments. There is a beautiful analogy given in Bruce Alberts in order to explain the slow addition as well as the fast addition. So, if the diagrammatic representation is, this is a free monomeric unit, free subunit, and a subunit which you will find in the polymer. This is the subunit in polymer. There is a slight structural variation. Now, if you look at, assume that this is the polymer, existing polymer. Okay, to this existing polymer, and if this is the plus end and this is the minus end, now imagine how this molecule has to be incorporated here. If this molecule has to be incorporated, now this is the shape of this molecule. It cannot be incorporated very easily. Okay, that's why this is a minus end or a slow end. Whereas, if this molecule has to be incorporated here, you see that it can be incorporated. As it is getting incorporated due to the hydrolysis, a variation can occur and it can fit in very well, and that becomes a fast growing end of the actin monomer. So this is how the polymerization, why this side grows faster, can be explained. What are the three things that we are learning from this actin myosin motor? Point number one, every step is fixed. So we have seen that the size is roughly about 11 nanometer size. We have also learned that ATP hydrolysis is important to drive this motor, and the force generated is used, and that is reflected in the force which is exerted by the myosin molecule. So we can easily calculate the speed of the motor. So the speed can be calculated by finding the number of steps taken, number of steps multiplied by the size of the step. So that will tell us the speed of the motor. And the final point is a concept of processivity. Its sustainability on a motor, how much it can travel without falling off. So these are the three things that we are learning from this translational motor, that is the actin myosin complex.